So we in the last session on heat, which was heat module 2, we were discussing about temperature. Then what are the devices which can be used to measure temperature? And we looked at different types of thermometers. We looked at mercury thermometer, alcohol-based thermometer, and a clinical thermometer, laboratory thermometer, how those thermometers can be used to measure temperature and so on. Now we are going to look at some of the effects of heat. So we have already looked at one effect, which is change of state in module 1, and also chemical changes in module 1. Now we are looking at physical changes, and that's where we talk about thermal expansion, right? So let us just look at what is thermal expansion and how that is important. So what is thermal expansion? So when there is heat which flows into a body, a body can go through physical changes, which is it can expand. So it can be expanding, or it can also contract. That depends upon whether, so if the body is getting heat, it is going to expand, and if it is losing heat, it is going to contract. So it depends upon what is happening. So you may be getting heat, that means you have kept it in contact with the hotter body, and since there is a temperature difference, that the heat energy can flow from the hotter body to the colder body, and in which case the colder body is getting heat, and as it gets heat, it will expand, right? Now, how much expansion does happen? That depends upon the type of body. So the amount of expansion which, for example, the iron goes through versus the amount so assume that I heat iron by 2 degrees centigrade, the amount of expansion it goes through, versus I take copper and heat it through 2 degree, and the amount of expansion that copper goes through, there could be differences because they are two different materials, they are two different substances, and it depends upon the amount of expansion that a material goes through depends upon the it depends upon it depends upon how much it depends upon the material, and the other aspect is what is the amount of increase in temperature that is going through. Those are two different important things, right? So the amount of expansion depends upon what material it is and how much is the rise in temperature has gone through. So the two important things. So these are the two critical aspects when you're looking at expansion. So now let me just revert back to the presentation which we were going through and look at thermal expansion. So I want to explain about some of the examples of expansion. Now, before getting into that, I want to talk about one more aspect. So when you say expansion, there are different types of expansion, right? So there are different types of expansion you talk about. One is called the linear expansion. Then there's something called superficial expansion. And then there is cubic expansion. So there are different types of expansion. Now, what does each of them mean? So linear expansion is increase in length. And superficial expansion is increase in area. I'll explain this again properly. and the cubic expansion is increase in volume. So let me try to explain what each of them mean. So let us look at linear. So what is linear expansion? Now let us say that I have an iron rod. So this is an iron rod, right? So this is an iron rod. And I heat this iron rod, so I keep it under Bunsen burner. So this is Bunsen burner, right? So, and this is a flame, right? Maybe I can use different color for that, right? So let me use red. So I have flame here. So this is flame, right? So this is flame. And now what happens to this rod when it gets heated? So what happens to this rod when it gets heated? So this rod will start. So when there is flame, definitely the temperature of flame is far higher. So the temperature of flame may be maybe 250 degrees centigrade. And the rod, before it was kept on the flame, was in room temperature. So it was probably 25 degrees centigrade. So there is a difference in temperature. So this is 250 degree, and this is 25 degree. The difference in temperature. So the heat is going to flow from the flame to the rod, and when the heat flows into the rod starts getting heated. So this is something that we have already seen, we have already discussed enough, right? When there is a temperature difference, the heat flows from higher temperature body to the lower temperature body. So here the flame is higher temperature and the rod is lower temperature. So the heat is going to flow from the flame to the steel rod, and the steel rod is going to get heated up. And because it gets heated up, since it's gaining heat, its temperature is going to go up, right? So its temperature rises. And when the temperature rises, it expands. It expands this way, right? And so that means its length is increasing. It expands and length increases. And this increase in length and that increase in length, right? So the increase in length is linear expansion. So I hope you understood what is linear expansion. So that increase in length is the linear expansion. So that is about linear expansion. Now let us look at the scenario where there's an increase in area when you heat it, when you're heating an object. And that is what is called a superficial expansion, as I explained some time back, right? So that is superficial expansion. Let us look at that scenario. When there is an increase in area, what happens? Let me change back to blue. All right. So let us take a disk. So this is a disk, right? So it's circular in shape, right? And it is made of, let's say, steel, right? So it's made of steel. And I heat it. So I keep it like this. So when this is looking at this way, let's say it's a plate. I'm sure plate is something which you may be aware of, right? So this is a plate. So this is a steel plate, right? And then what I'm going to do is I'm going to take the steel plate. I'm going to take the steel plate and I'm going to put it above the flame, right? So I'm putting it above flame. So I'll use probably again red, the same for showing the flame. So this is flame here, right? So I'm putting it above flame, and of course, and the flame is produced by a Bunsen burner, right? So So this is a Bunsen burner. So I'm keeping it above flame, which is produced by Bunsen burner. And when I heat it this way, what really happens to this plate is, plate expands in all directions. It expands like this in all directions. It's also called radial expansion. Now, I know that the immediate question that you'll have is, what is radial? You can only say that it is along the direction of a radius, and all this is direction of radius, right? All this is. So that is what is radial, right? So it is expanding this way, and then because of this expansion in all directions, what happens is the area is increasing. Area is increasing. All right. Now that is what is called superficial expansion. So when there is an area increase, expansion due to which there's area increase, that is what is called superficial expansion. And why I say the area is increasing is because it is expanding in all directions. So in fact, the radius. So before heating, the radius is R. After heating, it becomes maybe R1, where R1 is greater than R. That means we have got a bigger radius circle for this plate, and as you know, the area is pi into radius squared for a circle, and since the radius is increased, the area also is increased. So when I heat this plate, it goes through radial expansion, because of which its area is increasing, and that is what is called superficial expansion. So we looked at linear expansion, and this is superficial expansion where the area of the object is increasing. Now, what is the next type? Next type is cubic expansion. Now, what does cubic expansion mean? Now, let us look at a cube, right? So this is a cube. Maybe, let me just do it again. Okay, so let me draw a cube again. Does not. Right. So now, so I'll just draw a cube here. So let me use, okay. So I'm drawing a cube. This is a cube. So this is a cube, right? I know I've not drawn a perfect cube, but I sure that you understood. Now I'm taking a cube, right? Maybe this cube is made of probably is made of steel, right? So this is made of steel. And then what I do is I take this cube and I put it on again a Bunsen burner. So I'm putting this cube above Bunsen burner. So I use a Bunsen burner here to heat it, right? And I use a Bunsen burner to heat it. So here's a Bunsen burner. So this is Bunsen burner which I use here, and I heat this steel block. So this is a steel cube, right? So I'm using a Bunsen burner to heat the steel cube. And what happens to the cube is, now it's a three-dimensional object. Cube is a three-dimensional object, right? So, and it has got a length. So this is the length, and this is the breadth. This is the breadth, right? And this is the height. This is height. And the volume is length into breadth into height. I'm sure that you've learned this in 6th standard, right? Now, when I heat this cube of steel using a Bunsen burner, what happens is that it goes through a cubic expansion, which means the length increases. So the length increases, the breadth increases, right? And also the height increases. So everything is increasing. The length is increasing, breadth is increasing, and height is increasing. And because of that, we have a bigger length, a bigger breadth, and a bigger height. So when I write, so now the new volume V1 after expansion is L1 into B1 into H1, where L1 is greater than L, B1 is greater than B, and H1 is greater than H, because it is during the cubic expansion, length, breadth, and height, everything is increasing, and because of that, the volume is increasing, and you got a higher volume. So cubic expansion is an expansion where the overall volume of the object is increasing. So we have looked at all the three types of expansion: the linear expansion, right? We looked at linear expansion, and that is increase in length, right? Then we looked at superficial expansion, which is increase in area, and then we looked at cubic expansion, which is increase in volume. So these are three different kinds of expansion which a body goes through when it is heated. Now you should also understand there is also a reverse process of contraction when an object is cooled. And all these, so just like linear expansion, there could be linear contraction. Just like a superficial expansion, there could be superficial contraction. Just like a cubic expansion, there could be cubic contraction. So all reverse can happen when the object is losing heat energy. In this case, in all these cases, what I talked about, I was heating these objects and it was receiving heat. Now let me also tell you one thing. Even though the experiments which I showed was all using a Bunsen burner, as I told you before, heating doesn't necessarily mean you put a flame and heat it. Any point where one object is in contact with another object which has got a higher temperature, the body with the lower temperature is going to get heated, because the heat is going to flow from the higher temperature body to the lower temperature body. So heating doesn't necessarily mean you have to have a flame or a burner or something like that to heat the body. So please keep that in mind. All right, so that is about the different types of expansion. Now I'm going to talk about how this thermal expansion, this characteristic of thermal expansion can be made use of. There are different places where it can be made use of. And one place which is very, very commonly used, which has been used for hundreds of years, is to fix a steel rim on a wooden wheel. Now, why do somebody put a steel so usually you have the cart wheels. I'm sure you've seen the cart wheels, right? So this is a wheel like this, right? So this is a wheel and it has spokes like that, right? So it has spokes like that. So, and this will be made of wood, right? So this is made of wood. But as you know, this wheel is going to turn on ground, which could be rough ground, and so to reduce the wear and tear of the wood wheel, what used to be done was around this rim they put a steel around this wheel they put a steel rim. Sorry, it's not looking entirely circular, but really it's a circular. Okay, so they put a steel rim like that. So this is a steel rim, right, around the wooden wheel, and this steel rim will drastically reduce the wear and tear of the wheel, because the wood is now not directly coming in touch with the ground, but rather it is the steel rim, and the steel is far more harder and stronger substance, and so it doesn't go to the wear and tear like wood, which is not as strong as steel. So the steel rim is fixed around the wooden wheel. Right? Now, for doing that, for fixing this steel rim around the wooden wheel, we use this property of expansion. Right? So we make use of the property of expansion. So how do you mount this iron rim on the wooden wheel? Now, the very important part of this is we should be fixing the rim on the wooden wheel in such a way that the steel rim doesn't come off easily, because the wheel is going to turn at very fast speeds, and at that point there should not be any reason why the steel rim comes off the wooden wheel. So it should be firmly fixed onto the wheel. Now, how can you do that? That's what we're going to see here. So how do you mount this iron rim or steel rim on a wooden wheel? Right? So, sorry. So iron rim mounted on a wooden cartwheel has diameter slightly lesser than that of the cartwheel. Right? So what is diameter? Again, let me go back here. So what is diameter? So if you look at a circle, the wheel is definitely circular, right? And diameter is this, which goes through, it is the biggest chord of a circle which goes through the center, right? So this is a center, correct? So that is what a diameter is. So this is a diameter, right? And so the rim which we fix around the wheel, right? The rim which is fixed around the wheel. So this is the rim, right? Now this rim which is fixed around the wheel, its diameter, so this is D, assume, right, which is the diameter of the wheel. The rim diameter will be slightly less than D. So this rim diameter, assume the diameter of the rim is, so the diameter of the wheel is dW and diameter of the rim is dr, right? dr is slightly less than dW. Then the question will be, how the hell, right? Let me use that strong word. How the hell can that rim be fixed on the wooden wheel? Because you are trying to put something which has got a smaller diameter than the wheel on it. Is that possible? Because if it was elastic like a rubber, yes, it's possible. I can pull the rubber and put it on, right? That's definitely possible. But steel is not elastic. Steel is very hard, very strong. I cannot just pull it and put it on the wheel. So how do I do that? That is where the thermal expansion is going to help us, right? So let me just go back to the presentation. So that is where the thermal expansion is going to help us. So the iron rim is heated red hot. Sorry for the spelling mistake. It is RED, right? So iron rim is heated red hot, and when it is heated red hot, the iron rim expands, right? So that's basically what's happening. So just to go back, so the rim was, so let us assume this is rim, and I told you the diameter of the rim, let us call it as, the diameter of the rim is dr, and the dr, the diameter, is slightly less than the diameter of the wheel. Now what I do is, when I heat this, so I heat it, and I will show you a video on how the heating is done. So I heat it. At that point, what happens is that it goes through expansion, right? It goes through expansion. So it starts expanding in all these directions. And so when it expands, what happens is that after a while, once it's heated red hot, the diameter of this rim increases, and the diameter of the rim will be, almost equal to, a slightly more than the diameter of the wheel, right? So the wheel is not heated. Wheel is wooden wheel. It is there, right? I heat the rim expands, and it expands once it's heated red hot. The diameter of the rim will be slightly more than the diameter of the wheel, where I will be able to just slip it on to the wheel. And then what happens is and then I pour some cold water on the rim now is getting cooled, just the opposite of heating. And when it gets cooled, what happens? It contracts. It just goes the reverse way. And when it contracts, again, its diameter becomes slightly less than the diameter of the wheel, and then it just presses onto the wheel, right? As it contracts, it just presses onto the wheel, and then it is held rigidly, and it never comes off after that. It is this particular process in mechanical engineering is called shrink fit. It's called a shrink fit. There's something called a shrink fit joint, which is very often used for fastening things together in mechanical engineering. So if any of you tomorrow becomes mechanical engineers or civil engineers, you'll definitely learn about what is a shrink fit joint. It's a very important concept, right? So let us just go ahead with this presentation. So now iron rim is heated red hot. The red hot rim is lifted by fire tongs and slipped over the wooden cartwheel. So I heat it, and because of it's heated red hot, the diameter of the rim increases, and then I'll be able to easily slip it on the wooden wheel, right? When it's red hot, and it easily slips over because of expansion, right? And then what do I do? Then I pour cold water on the rim, and when I pour cold water on this hot steel rim, then it contracts, because now suddenly its temperature is going down, and when the temperature is going down, the reverse process of expansion happens, which is contraction. So it contracts and it tightly fits onto the wooden wheel. That's basically what happens. So I want to quickly show you a video which explains this specific aspect. Uh, just a moment. So this is what I want to show you. So now what is being done here is it's being heated red hot, right? So being heated, and it's heated to a temperature of almost 600 degrees it's kept inside fire, which is almost 600 degree Celsius temperature. And now you can see what is happening. They are able to slip it in onto the wooden wheel. So here, that's what they're doing, right? They are slipping it onto the wooden wheel, right? So you can see that they're slipping it on. So they are just hammering it in, and they're slipping it onto the wooden wheel. And why they're able to do is because the expansion, right? So the rim is expanded, right? So rim has expanded, and because it is expanded, they're able to just slip that onto the wooden wheel, and then so they easily slipped it on. So they're just hammering it a little bit, but it's not too hard. They're using fire tongs. This is what he's holding on, right? This is what he's holding on is called a fire tong, right? So this is fire tongs. It is used by people. It's used by smiths for holding hot metal. So that's just a fire tong. So he's using a fire tong and holding and just hammering it a little bit so that it slipped on to the wooden wheel. Right. So go ahead. So he just slipped it onto the wooden wheel, and then what he's going to do? Now, then you can see that he's pouring a lot of cold water on the rim. And at the point when it is cold, when the cold water is poured, what is going to happen is it is going to contract. The rim is contracting. And when it is contracting, what happens is it presses onto it fits onto the wooden wheel. It just contracts radially and it just tightly fits onto the wooden wheel. Tightly fits, tight fit on wooden wheel. Right? So that's what's happening. And now you can see that nothing happens to that iron rim, steel rim. It's strongly, tightly fitting onto the wheel, and then we can actually use that. So you can see many wooden wheels, and all of them having the steel rims on it. So I hope that kind of got you an understanding of how the expansion is made use of here. Let us go back and look at an experiment, right? This is called the Greaves-Sand's ring and ball experiment to prove that metals expand. So this is a pretty popular experiment called the ring and ball experiment, which can be used to prove that the metal expand. So let me just show you a diagram which kind of shows the setup of this experiment. Right, so you can see what you have here, right? So what we have here is we have a stand, right? And stand has got a ring. So there's a ring and there's a ball here. And initially what the situation is that the ball can pass through the ring. So here the ball is able to pass through the ring, right? That means the diameter of the ball is maybe equal to or slightly less than the diameter of the ring, and so because of that it's able to pass through the ring. Now what you do is, so that is before heating. Now what you do is you hold on to the chain that you have and keep the ball above a Bunsen burner and just heat it for 5 minutes. After 5 minutes, what happens is the ball goes through expansion. In fact, it's a cubic expansion. It expands in all directions and it expands. And after the expansion, when you again try to pass it through the ring, the ball does not pass through the ring. Right? And why it doesn't pass through the ring is because the ball has expanded. So expand, right, after heating. So that is basically what the experiment. So this experiment is really proving that the metals expand, right? So let us just go through let's just go through the let's just go through this experiment step by step, right? So metal ball is suspended on a metal chain, right? So that's what we've seen, right? So the metal ball is suspended on a metal chain. So metal ball is suspended on a metal chain. So this is what it is. So the metal ball is a metal ball which is suspended on a metal chain. The metal chain is attached to a hook on a steel stand. So this is a hook which is attached on a metal stand. So this is what the arrangement is. Initially, the diameter of the ball is equal to the internal diameter of the ring. So initially, the diameter of the ball. So this is the ball. Diameter of the ball is equal to the diameter of the ring. So because of that, the ball easily passes through the ring. Right? Then what you do is you heat the ball for 5 minutes by holding the chain. So I hold the chain and keep the ball above a Bunsen burner and heat the metal ball for 5 minutes. And then once that heating is done, if you try to pass the ball through the ring, it won't pass through it, right? So when you try to pass the ball through the ring, you'll find that it doesn't pass through, and that is because the ball is expanded, and then and because of the expansion, its diameter is increased, and because the diameter is increased, it's not able to pass through the ring. Now, if we allow the ball to cool for 10 minutes, what happens to it? It is going to lose all the heat, right? Because now it is very hot, maybe it's 80 or 100 or 110 degrees centigrade, because we had kept it above flame. Now it will start, if you're allowing it to cool down, the outside room temperature is 25 degrees and the ball temperature is 110 degrees. So its temperature is higher, so it starts losing energy because it's got a higher temperature, and slowly the temperature goes down. And when the temperature goes down, what happens to the ball? It starts contracting. So after 10 minutes, what happens if you try to again pass the ball through the ring? You'll find that it will pass. The reason is because it is contracted back to the diameter it had before. So that is what the experiment. So this experiment shows that based on increase in temperature, the metals expand, and because of decrease in temperature, the metals contract. Now I want to show you a small video which shows this experiment pretty neatly. So here's the experiment. So you have this is the ball, and this is the chain, and the chain is attached to the steel stand. And you can see before heating, the ball is passing through the ring. This is because the diameter of the ball is less than the diameter of the ring, right? So it's easily going through the ring without any problems. Now what you're going to do is you can hold on to the chain and you can heat the ball. So he's keeping it about gas burner and heating this ball. Now when you are heating the ball, what happens is the ball starts expanding, and after some time you'll find that the diameter of the ball has increased more than the diameter of the ring, and so it's not able to pass through the ring. And that's because of expansion. Now if you allow the ball to cool down, it again passes through the ring. So it shows that when you're heating the ball, it is expanding, and when it is allowed to cool, its diameter is contracting, and that actually shows how this whole thing works. All right, so that is an experiment which shows that metal expands when it is heated and it contracts when it is cooled. Now, the other important aspect which I want to talk about is the difference. I want to talk about is the difference in level of expansion between different solids. So, as I told you, the amount of expansion which something like a steel or iron has versus the amount of expansion. So, assume that, let me go back here and use a whiteboard. So, assume you have a steel rod. You have a steel rod, and you also have a brass rod. Brass is another metal. In fact, it's what you call the alloy, right? And you'll learn about this in chemistry. Alloy is made of multiple metals, so it's actually a mix of different metals. That's what alloy is. So don't worry about it. Just consider that brass is a different type of metal. So now you have steel rod and you have brass rod. Now I increase this. I heat the steel rod through 50 degrees. So that means, the steel rod's initial temperature. Let me just erase this. So initially its temperature was room temperature, which was 25 degrees Celsius, and now I have increased it to 80 degrees Celsius. So it has gone. Temperature increase is 55 degrees Celsius, right? Now, then definitely it goes through linear expansion, right? That's something which I explained. So it goes through linear expansion, its length increases, Now, same thing I do with the brass rod. So it was in 25 degrees Celsius, I increased it to 80 degrees Celsius. So brass also has gone through increase in temperature of 55 degree, and so brass also go through linear expansion. So both of them go through linear expansion, but the amount of expansion, will not be the same, will depend on the material. So here the brass in fact will go through more expansion than steel. Steel will not be expanding as much as brass, even though the temperature increase is the same. So brass has gone through 55 degrees Celsius increase in temperature. The steel rod also has gone through 55 degree Celsius increase in temperature, but brass will expand more than steel because the expansion, the amount of expansion is definitely a property of the material, right? So I want to kind of prove that. I want to show an experiment where I can show that the amount of expansion depends on the material, right? So that's what this experiment is all about. So now how can I show that? For that, I need to explain to you something. I want to explain to you what do you mean by a bimetallic strip, right? So I want to explain to you what do you mean by a bimetallic strip. So here you can see this is actually a bimetallic strip, right? So, and you can see two things. Invar is, you can say it's steel, right? So assume it's steel, right? So it's again an alloy. Brass is also an alloy, and I explained alloys are nothing but metals which are made of, which is a mix of different metals. So that's what alloy is, right? Now, so this is a bimetallic strip. So this is what is called a bimetallic strip. Why it is bimetallic? What does bi mean? Bi means two. So here it has got two metals. There's one strip of invar and there's another strip of brass which are bound together. So there are two different metal strips bound together. That is what is a bimetallic strip. Two different metal strips bound together. That is what is a bimetallic strip. So you have one strip of invar and the other strip of brass which are bound together, and that's a bimetallic strip. And now what you're going to do is you're going to heat it. When you heat it, what happens is, you can see on heating, it shows on heating what happens. When you heat it, brass expands more than steel. And because the brass expands more than steel, it bends. It bends, and it bends in such a way that the brass has got more length than steel, right? So it bends towards steel. And when you cool it down and when it contracts, what happens is that the brass contracts more than steel. So it bends the other way. So bimetallic strips are this particular property of bending of bimetallic strips when I heat it is used for creating or making different devices. We'll actually discuss about that later on. But this particular property, this behavior of bimetallic strips shows that different metals will expand. The amount of expansion will be different based on what metal we're talking, right? So that is about the bimetallic strip. Now let me go back to the presentation and discuss further. So bimetallic strip has two strips bonded together. One strip is made of brass and the other strip is made of steel. Invar is kind of a steel, I can say, right? So you have got two different metal strips you're bound together, and that's why it's called a bimetallic strip. Now what I can do is I can hold the handle of the strip and heat using a Bunsen burner, And when you heat, what you can find is, since the brass expands more than steel, the bimetallic strip will bend or curve towards the steel side. So I want to actually show you the experiment. Um, Now here is the experiment which kind of shows this property of bimetallic strip. So now here is the burner, and here is the bimetallic strip with the handle, right? So the professor is taking the bimetallic. This is a bimetallic strip, and in fact, as I showed you in the diagram, this in fact has two metallic strips. One is with brass, and the other is with steel, which are bound together, right? Using some mechanism, it has been bound together. So it is a bimetal strip, which got one steel strip and the brass strip, which are bound together. Now she is going to heat it. She's going to keep that above the flame and she's going to heat it. So see, she's kept it above the flame. And let's see what happens when she keeps it above the flame. So she's keeping it above the frame. You can see what is happening. It is bending, right? So you can see it's bending. Don't you see that? It was absolutely straight before, and now it's bending, and it is bending, and this side that you're seeing now, the side that you're seeing now, is brass, and the other side is steel. And the brass expands more, so it'll bend towards the other metal strip, which expands less. So it's bending towards the side where there's steel, right? Because brass expands more than steel. So this is what you see here. And as in going, giving more and more temperature, more and more heating done, it bends more and more because its temperature goes up. And as in when the temperature is going up, it expands more and more. And so you can see that it really completely bends. So you can see how much it's bending. It's bending quite a lot, right? Really visibly bending. It's almost become like a curve, right? From a completely straight strip, it has become a curved strip. So this is showing how a bimetallic strip behaves, and why it is behaving so is because the amount of expansion which brass is going through is higher than the amount of expansion steel is going through, and that's why it's bending. So this experiment proves the fact that the amount, and at the same time you should understand both steel strip and the brass strip has gone through the same increase in temperature, right? So the increase in, because both have been kept together on the same flame, so the increase in temperature is the same, right? It's the same, but the amount of expansion is different. So that is why the amount of expansion of is completely dependent upon the material and or the type of metal that we're talking about. So that's what this experiment is proving. So when the brass expands more, since the brass expands more than steel, hence the strip will curve towards the steel side. And that's what we saw now, right? And I think we saw this already. That is how we can fix the iron rim on uh, a wooden wheel, right? A cart wheel. Now, another use of thermal expansion is what we call riveting. Riveting is a very common usage, and it's very commonly used in fastening things together. For fastening in the sense that I want to uh, you know fix two things together, then I can use a rivet. Let me show you the diagram and see. Let us see how the rivet looks like. So here you have two metal iron pieces, and I wanted to join the iron pieces. So these are the two, and this is a join, right? So you can see this is where the join is. And here is the join. So this is a join, right? So I'm joining the two metal pieces and I'm using a rivet for doing the join. Now, what usually is done is I will use a rivet. So this is a rivet and this rivet is going through. So there is a hole here. So there's a hole made here on this steel piece, iron piece, and there's a hole made in this iron piece too. And you are putting this rivet through the hole, right? And now the way we design this rivet is that the rivet length is slightly smaller than the thickness. So this is the thickness, right? So this is thickness. Let me call the thickness T, right? Now, what you do is the rivet, what I use, so rivet is, it will look like this. So this is how the rivet looks like, right? So, and this rivet, this length of the rivet, let me call it L. This length L, right? Length L will be slightly less than thickness T. That's how I will make the rivet. Then what I do is I heat the rivet. When I heat the rivet expands, right? The rivet expands, and when it expands, what happens? The length will become slightly greater than the thickness. So that is how you are able to see it outside, right? So the length is slightly more than the thickness, so it'll slightly come out. So now I put the rivet in, and then I hammer it. I hammer it, and when I hammer it, it becomes like this. Now what I do is I just allow it to cool. Maybe I can pour some water too. I allow it to cool. At that point, what happens is the length now reduces. It contracts. And when it contracts, it leads to, again, a tight fit, right? So it leads to a tight fit. Exactly same principle as the principle that we used in the case of the steel rim around the wooden wheel, and how we tightly fixed it onto the wooden wheel. The same thing, we expanded the rim, put it onto the wooden wheel, poured cold water so that it contracts and it gives a tight fit. Same thing here. The length of the rivet is slightly smaller than thickness. I heat it, it expands, so that, and I heat it to the extent that the length becomes slightly more than thickness. Then I hammer it, right, when it is red hot. Then I pour some water and allow it to cool. Then it contracts and leads to a tight fit. The exact same concept that we have used in the case of a steel rim, which we'll use here too. Right? So, the rivet is a small steel cylinder used for fastening two metal strips. That's what I showed you in the diagram. Hole is made between the two metal plates. So a hole is made, and through the hole is what you pass the rivet. I'll show you a video which kind of explains it a little more better. Rivet is chosen such that the length of the rivet is slightly smaller than the thickness, as I explained. Right, so the length of the rivet is slightly smaller than the thickness and of the plates. The rivet is heated red hot till its length becomes slightly more than thickness, because of the linear expansion, right? When you're heating the rivet, it's got linear expansion and becomes slightly more than the thickness of the plate. And then while red hot, is picked and using a fire tong, and it's inserted on the hole and hammered and flattened on the other side, as we'll see in the video. And then the rivet is cooled down. At that point, it contracts because its real length was less than the thickness of the metal sheet, and so it leads to a tight fit, and so the two metal strips are tightly held together. because of the contraction. So the same principle that we used in the steel rim, I want to show you quickly a video which explains this. So you can see that here using a fire tongue, see, you can see that now, in fact, probably the video is not as clear, but I want to just, so this is one steel strip, so this is one steel strip, right, and this is the other steel strip which they want to join using the rivet. So already you can see some rivets have already been fixed. Now this is new rivet that he's fixing. So what he has done here is, now the thickness of the two plates, so in fact here it's like this, so you have one plate here like this, so one plate is here like this, and that other steel plate is like this, right? So, and we are trying to rivet this together, rivet like this together, so that you're fixing and the rivet passes through like this, right? So we're trying to fix this plate onto this plate. So that's what we're doing here. So I think that you're clear about it. Now what we've done is we've taken the rivet, we've heated it red hot, and because it is heated red hot, you can see that the rivet has expanded and its length is increased more than the total thickness. So total thickness is this much. This is a total thickness, right? This is a total thickness, and you've heated such that the rivet comes a little bit out. So it's coming a little bit hard. Now this rivet is very thick in diameter, so I cannot use a hammer to do it, and in fact instead I have to use a hydraulic press. So in fact this is what is called a hydraulic press. Now you may have two questions here. One question is what is hydraulic, and second is what is press. I am sorry, I cannot answer that question, because for learning hydraulic you need to learn what you call fluid mechanics, right, which you will learn later on, but let's not bother about it right? So, but this is a hydraulic press using which they are going to apply pressure on to the rivet to flatten it, right? So that's what you can see in the video. So let me play the video now. So now he's holding and he's bringing the press, and he's going to press that to flatten the rivet. So it's flattened. Now that's done. Now when this rivet cools down, right, so now he's doing the next one. Red hot, right, now he's going to press it down, flatten it. The next rivet also done. Now what happens is these rivets will cool down, and when it cools down it contracts, and then that leads to a tight fit, right? So I hope you're clear about rivet. Riveting is a very common way of fastening things together, to tightly hold things together. And so I hope it's clear what riveting is from this video. And again, we are using the same thermal expansion contraction concept for our benefit to get that done. All right, so let me go back to the presentation. Now I want to talk about railway tracks, right? Again, in railway tracks, you need to consider, when you're laying the railway tracks, you need to consider the same aspect of expansion and contraction, right? Now, I think I will stop the session right now. I'll continue with, I've got a few more areas to discuss on the thermal expansion. I'll continue the session, but you know, I think we have covered quite a lot of portions today. So I hope it was interesting, and I hope you understood what is thermal expansion, what are the different types of thermal expansions, which is linear, superficial, and cubic expansion. We looked at the Gravesand's ball and ring experiment, which proves that the metals expand and contract. When they're heated, they expand. When they cool down, they contract. We looked at the amount of expansion depends upon the type of metal, and that is where we used the bimetallic strip and heated it and showed that it bends because the brass expands more than steel, and so it was bending towards the steel side, and that kind of proves that the amount of expansion depends upon the material. Then we looked at some areas where the thermal expansion can be made use of. First thing that we looked at is the how a steel rim is fixed onto a wooden wheel. Then we also discussed about riveting and how the riveting works, and how the thermal expansion contraction is used in rivets to get a tight fit. So with that, I'm going to stop and let us continue with the remaining interesting topics regarding thermal expansion in the next session. Thank you.